Hi, I'm Bowden, a developer advocate here at Firebolt, and welcome to FireEdge. Today, we'll be talking about distributed query processing. Firebolt is a cloud data warehouse, and in order to efficiently process large data volumes, we need to be able to process a single query across multiple machines. For a query engine, doing this both quickly and correctly isn't easy, which is why I'm going to show you how it works underneath the hood. Let's get into an example. In our hypothetical SQL query here, we're calculating the volume of orders across a couple of different countries. I've written some sample data here on the board for you to look at. Now, the first thing the query engine will do when computing this query is it'll calculate the results of the inner join. That'll be ID, name, and price. Now, we'll have our two rows from the US orders, and we'll also have our one row from the German order. This is the intermediate query results. It's the first step in the query process, and it's what happens before we compute the sum aggregate of the query. This will then be aggregated using that sum function, where our one row from Germany will remain the same, and our two rows from the US will be compacted into one, where our price will then be that sum of 19. Now, the hard part is, how do we do all of this when we have multiple nodes in our cluster? We want to make sure that we compute the correct results, and in order to do that, the data we're computing with needs to be co-located on the same node. In order to achieve this, Firebolt uses something called the shuffle operator. The shuffle operator reads in a row, looks at the data in individual columns, and then deterministically places that row onto one of the nodes in the cluster. In our example here, the shuffle operator would be looking at the join key, which is the ID, and routing data onto specific nodes based on the ID present. So in this example, we might read data with ID1 representing the US and put that onto one node in the cluster, and then read data with ID5 representing Germany and route that to a different node in the cluster. This way, each individual country is mapped to a specific node, and then we can compute the joins and aggregations. With the shuffle done, the join can happen in a fully scaled out way, with different nodes in the cluster handling different parts of the join. In our example here, one node would compute these two rows in the join, and another node would compute this row in the join. Now, the next step in query execution would be to ensure that the group by keys are co-located on the same node in the cluster, and then compute the aggregate. In this instance, because our group by key is the same as our join key, we wouldn't need to do this, and Firebolt would avoid adding in an unnecessary shuffle operator. As a user of Firebolt writing SQL queries, you don't actually need to be aware of this. Firebolt transparently inserts shuffle operators to ensure correct results, and has a number of optimizations that ensure that we don't add unnecessary shuffle operators and avoid unnecessary work as part of query execution. Alright, now let's try this out in Firebolt. I've translated that query that we had on the lightboard into Firebolt itself using the TPCH dataset with 100 gigabytes of data in the table. Our query is relatively similar. We're selecting the sum of prices of items that are relatively expensive, joining from the line item table onto the supplier table based on the matching key. Now, I have a one node engine running right now, and we can run this query using that engine. As you can see, Firebolt immediately gets to work scanning gigabytes of data, and in a little more than 1 second, we're able to return our results. Now, if we take a look at our query profile and look through all of the operations being done in Firebolt, you'll note that there are no shuffle operators. This is because this query was done on a one node engine. That means that no data had to be sent over the network to coordinate between different nodes. The optimizer removed any shuffle operators and made sure that we could maximize performance on this single node. I've now moved us onto a two-node cluster. This means that there is going to need to be some transmission of data over the network, and the shuffle operator should be in effect. It also means that we have double the computing power, and the query should execute close to twice as fast. So let's run the query again, and you can see this time, instead of taking 1.35 seconds, we've taken 0.71 seconds, nearly a 2x improvement. And if we check out the query profile, we're going to see a couple different shuffle operators. The first, towards the end of the query, is actually called a gather shuffle, where we're combining the results from the two nodes and returning it to the user. But you can also see if we keep going down the query plan, we have a shuffle that happens before the aggregate merge to make sure that we're computing the correct results and getting the correct sum of the values that we've queried. I've now swapped us to a 4-node engine. That's twice as many nodes as the previous query and 4 times as many nodes as the original query we ran. With this much more computing power, we're going to be demonstrating the power of scale-out distributed query processing. By adding more nodes to our cluster, we're able to distribute the work and speed up our query processing times. It's not going to be exactly a 2x improvement, but if we run this query, you can see that it takes 0.42 seconds, nearly a 2x improvement from the 0.71 when we had a 2-node cluster. Now, if you check the query profile, you'll see that the shuffle operators are right where they were before. We're just shuffling between 4 nodes instead of 2. If you want to learn more about the shuffle operator or go a little more in depth, we have a technical blog on the topic linked in the description below. Better yet, you can try it out for yourself with $200 in free credits today.